Let's look now at specifically simple harmonic motion with a mass spring system when we have the spring hanging from something so that it's vertical. And you might wonder, why is this different? We already did the horizontal springs. Why is this different? Well, there's two things that I think you'll find different about these problems. One is that these problems, they might try and be a little sneaky here and not give you maybe the spring constant. You have to do a little work to find the spring constant. And the second thing is that we've got an extra force and we've got an extra gravitation, or an extra energy type, both from gravity, that we have to consider. And so that can complicate things just a little bit. So let's look at this in general first, and then we'll do an example problem with this. So here's a pretty common situation. Maybe they tell you that we have a spring that's hanging from the ceiling or hanging from some surface without any weight on it, and then we put a weight on it and it gets stretched out. So originally the spring is this long. When we hang that weight from it and let it come to equilibrium, now it's this long. So you can figure out the spring constant from that information. That's usually how these are set up. Maybe they give you the mass for this thing and how far this gets stretched, and you can figure out what the spring constant is by looking at the force that's being applied to the spring, just the same as the weight of that block. So mass times acceleration of gravity there. That would have to be equal to the spring force if it's in equilibrium at this spot. So we know the spring force, we know the distance that this thing is stretched. Sorry, that'd be this distance here. The change from this length to this length would be this distance. And so we can use Hooke's law to solve for the spring constant. Now, we need to pay attention to that spot where the spring was to begin with, because that is going to be our unstretched length. And then we've got this other spot here that's going to be important. That'll be our equilibrium here. And then we've got one more spot that's important in terms of energy stuff, and that's what will probably make sense to define as our low gravitational energy spot. And that's going to be the lowest point that it gets to. Now remember, with gravitational potential energy, you could set that 0 spot anywhere you want, but just for the sake of keeping numbers positive, I usually like to make the low point be my 0. So at this point, UG equals 0. Alright, and so I'm going to need to make some measurements throughout here. Like once I actually start this thing moving. So the next step I want to do is, we've got this hanging at equilibrium, we pull it down, and then we release from rest, or maybe we lift it up and we release from rest, or we give it a push so it starts at a velocity that's given to us, something along those lines. But from here on to the right, we have simple harmonic motion, and it's going to repeat itself, so we don't need to show more than just bottom point, middle point, and top point here. When we go to look at energy, though, we need to make some measurements for each one of these. So first off, for gravitational potential energy, we're going to have 0 at this point. That's what we define to be 0. For the next point, we'll have mass times acceleration of gravity times this distance. That'll be our delta y here. And then for the third one, we'll have mass times acceleration of gravity times this distance. So there's our delta y. And then for our spring energy, we're going to measure from our relaxed length. So this distance right here would be the x that goes in for our spring energy. And then this distance here, x. And then this distance right here. And then this distance right here. And I guess I shouldn't have done that one here. We're not measuring the energy on that one yet. That's before our simple harmonic motion starts. Alright, so you can see in this case we've got spring energy the whole time, because that spring is stretched out the whole time. So that's a little different from our horizontal problem, where our equilibrium position was when the spring wasn't stretched or compressed. Well, now it's stretched out the whole time, so there's always spring energy present in these problems. There's also always going to be a spring force present that changes in size while the gravitational force stays constant. And then the last thing we need to look at here, of course, is kinetic energy. Kinetic energy is going to be 0 at this point and at this point where it stops and turns around. It will be a maximum right here. So let's just make some quick graphs about energy. So for gravitational potential energy, as I said, we start with no gravitational potential energy. We define it to be 0 at that lowest point. You could have it defined to be 0 somewhere else in the motion. That just means you're going to end up with a negative gravitational potential energy at some spot, which is fine. Then at the next spot, the equilibrium spot, we've gotten up to some height, delta y. That's half the maximum height that it's going to achieve. And then over here on the last one, we have double that equilibrium height. So we're going to have a gravitational potential energy that's twice as tall. For spring energy, that'll be at a minimum over on this one. Notice though that it's not at 0 even when it's at a minimum. So for spring energy, we're going to have a little value there, and then we get stretched out a little bit further, and so our spring energy is going to be bigger over here, and then it's going to be a maximum over on this side. And then for kinetic energy, we have 0 on both of these when it's stopped at the top or the bottom, and then we have a maximum value right here. Now thinking about the values for these ones, when we look at that first problem, the only energy type we have there is spring energy. And that's going to be useful when we do conservation of energy stuff, but we should try and make sure that our other graphs add up to this amount of spring energy that we have at this point. So I'm going to make that a little bit taller just so it fits with this graph, and then it looks like my gravitational energy maybe should be a little bigger over here, but you get the idea. The point is not to have the graphs be perfect here, but to just be able to recognize what types of energy we have at different moments in time. And then at any other moment in time on this, other than at the bottom point, at equilibrium, or at the top point, we'll have some mixture of gravitational potential energy, spring energy, and kinetic energy. And so that's the topic for our example problem. So let's look at that next. Here's our example problem. Why don't you take a minute to read through this and just think about your approach. Go ahead, take a minute. I will wait literally as long as you keep this video paused. Okay, good work. On this problem, we're going to solve using conservation of energy. Now, I know that we're going to have oscillations between kinetic energy and gravitational potential energy and spring potential energy. I need to figure out how much kinetic energy it has at this moment, 2.2 seconds after it's released. And in order to figure that out, I'm going to need to know how much energy is in the system altogether. So find some moment where I know everything I need to. And then I also need to know how much energy is in those other types, the spring potential and the gravitational potential energy at that moment in question, the 2.2 seconds. Now, in order to figure that out, I'm going to need to know where this thing is. I want to know where a simple harmonic oscillator is at some moment in time. I can write an equation for that in the form f equals a cosine 2 pi f times t. Alright, so I need to figure out my amplitude first. That one's pretty easy. That would be 0.25 meters. That's how far it's been lifted from equilibrium before it's released. Cosine of 2 pi. Oh dear, I don't know the frequency. But I do know that frequency is equal to 1 over the period. I don't know the period. But I do know that the period for a mass spring system is equal to 2 pi times the square root of m over k. But I don't know the spring constant. But I do know that this thing is at equilibrium when the spring is stretched by 0.5 meters. So at that location, my net force is 0. That means my gravitational force has to be equal to my spring force. So m times g has to be equal to k times x, the distance stretched. Alright, so now I can rearrange and solve for k, and I get mg over x equals k. M times g, that's 0.5 times 9.8 meters per second. 0.5 kilograms times 9.8 meters per second squared, divided by the distance stretched right then is 0.5 meters. Oh, that's convenient. So I've got 0.5 on top and on bottom, so that'll leave me just with 9.8 newtons per meter, which is K. Alright, now I know my value for K, and so I can then figure out what my period is going to be. And let me get a little workspace here. There we go. Alright, so the period then is going to be 2 pi times the square root of 0.5 kilograms over 9.8 newtons per meter. And so my period in this case is going to be about 1.42 seconds. And then frequency is going to be 1 over 1.42 seconds. So my frequency is going to be 0.705 hertz. Okay, so over here, that means that my equation for motion is x equals 0.25 meters times the cosine of 2 pi. Oh, let's start that up here. Hold on. 2 pi times 0.705 hertz times t. Alright. Now I want to know where it's going to be at that time of 2.2 seconds. So I'll plug in x equals 0.25 meters times the cosine of 2 pi times 0.705 hertz times 2.2 seconds. And then it'll be 2.2 seconds. And then I go to my calculator and, ooh, this 2 pi, that reminds me, I should double check and make sure my calculator is in radian mode. Alright, calculator's in radian mode. And I'll enter all this and I get an answer of negative 0.237 meters. It gets down as far as negative 0.25 meters, so I see I'm almost at the bottom here. I'm going to expect a pretty slow speed if I'm all the way down there. Alright, so now we know where the object is. Let's figure out energy stuff here. And I think with all the measurements we have to make here, we definitely are going to want a picture of this. So here we see the mass in question where it's at that 0.237 meters. That was a negative, so that meant below equilibrium here. If you're not sure whether that means below equilibrium or above, just plug in a time of 0 into your equation for position. This one gives us a positive 0.25 meters, and it says that we lift this thing up by 0.25 meters to begin with. So we know that it's above equilibrium to start. So positive must mean above equilibrium, negative must mean below equilibrium, this problem. So we're below equilibrium. We're going to have some amount of kinetic energy, some spring energy, and some gravitational potential energy. We need some other point in time to compare this to. I would tend to go for a point in time where we have just one type of energy present, if possible. if we can calculate that value anyway. And from the past, the previous page, what we saw was that if we look at that moment when it's all the way down at the bottom, as stretched out as it can get, at that moment we've gotten lots and lots of spring energy, but we have no gravitational potential energy, at least if we define it to be 0 at that spot, and we've got no kinetic energy. It's at rest there. So this will be all the way at the bottom, which is 0.25 meters. And it wouldn't be a bad idea to just mark that location for future reference. This is our UG equals 0 line. Okay, and then we've also got another one up top that we should be aware of, and that's our place where spring energy would be 0. And so that's going to be, well, let's see. We had a spring that was 1 meter long, and then we put a weight on it, and it came down to 1.5 meters. And so that's our equilibrium spot, is 1.5 meters below where the spring was anchored originally. So where that mass would be if the spring wasn't stretched out at all, that'd have to be 0.5 meters above equilibrium. So I'll try and sketch that in here. This is our US equals 0 line, and that's going to be a distance of 0.5 meters above that equilibrium position. So we had an unstretched spring, which was 1.0 meters long, and that's the spot where we have no spring energy. We put that weight on there, and it became 1.5 meters long, so we know there's a difference of 0.5 meters in those two distances. So from equilibrium to where that spring was originally, that's our 0.5 meters. And I'm going to need to make some measurements from both of those here. So for this one, I'll be interested in this measurement, and I'll call that my X initial for the spring energy equation. And for this one, I'll make that measurement, and that'll be my X final for the spring energy measurement. And then also we're going to have a distance right here, and that'll be our delta Y for that moment in time. And at the beginning, we'll have 0 for delta Y on this one. All right, so we're set up for conservation of energy now. Let's go ahead and write an equation for this. The conservation of energy equation is always written about the same way, so the total energy doesn't change. So our starting total energy and our ending total energy have to be the same values. What changes is the next step, where we fill in the types of energy we have at each moment in time. So on our initial side, I'll say that's the left-hand picture, we've got no motion, so no kinetic energy. We've got it as low as it can get. We're calling that 0 gravitational potential energy. So we're going to have nothing but spring potential energy here. So that'll be US initial. On the right side, we're going to have all three. It's moving, so we've got kinetic energy. It's also above that 0 gravitational energy point, so we're going to have UG final. And the spring is still stretched out, so we're going to have US final. And then we can fill in equations for each of these. So US is 1/2 times the spring constant times X initial squared. Don't forget that squared there. That's an easy one to miss. K final will be 1/2 m V final squared. That V final is what we're looking for here. UG is going to be mass times acceleration due to gravity times the change in position from our 0 point there, final. And spring energy again is 1/2 K X final squared. And we can figure out everything here except for the speed, the final speed. So let's go ahead and plug in and solve. So we'll have 1/2 times our spring constant. We calculated that earlier. That was 9.8 newtons per meter. The distance stretched to begin with, well, that would be this whole distance here. Oops, I guess I already had that drawn. That was the xi. And I see that it's 0.5 meters down to equilibrium and another 0.25 meters down to that location. So that'd be 0.75 meters at this point. And then we'll have our 1/2. And the mass is 0.50 kilograms. And V final squared stays as a variable. And then we have our mass times acceleration of gravity times delta y, so that'll be 0.50 kilograms and 9.8 meters per second squared. And our delta y there, well, that's going to be 0.25 meters from equilibrium down to our 0 level. But we're not down all the way there. We're only down 0.237 meters from equilibrium. So that must mean that we are 0.013 meters above that 0 energy level. Okay, and then one more term here. We're going to have plus 1/2 times the spring constant was 9.8 newtons per meter times the distance stretched there. Let's see, we got 0.5 meters to go from the 0 level for spring energy down to equilibrium, and then another 0.237 to get down to where that spring is. So the spring is altogether stretched out by 0.737 meters, and that will get squared. Now we've got just algebra. So let's figure out what we get as a result here. So on the left side we can see that we have 2.76 joules altogether. That must mean the right side is going to add up to 2.76 joules as well. That spring energy term is still very close to 2.76, so most of our energy is still in that form. We have a little bit of energy that's changed into the gravitational potential energy, and if we look at the amount left for kinetic energy, it is tiny. So we're going to get a little teeny tiny speed, but that's okay. That's what we expect when we're close to that point where it's going to stop and turn around. So now let's finish the algebra and solve for V. And we come out with a final speed of 0.35 meters per second at that spot. So very slow. That fits with our expectations. On a problem like this, there really is a lot to consider in terms of the energy stuff. And so the problems where we do have to do conservation of energy do tend to be the horizontal spring ones, where we don't have gravitational potential energy changing, so we don't have to think about it. But if they throw one at you here on the AP test, this way you've seen one, you have an idea of how to set that up. So hopefully you found this useful. If so, please like the video and share it with anyone else you think that would find this useful. And if you think you'll find other videos of mine useful, please subscribe to the channel. Thanks very much for watching.